te dire, à mon avis, c'est ce qu'on fait.
D'accord. Voilà, donc pour passer à la suite.
Time that was not possible, so we decided to look what was happening in the field and see what the main problems were and what people were trying to do, and provide sort of a medley of algorithms that people could use on or off the field. So the way I've broken down this talk is initially I'll give you a brief overview on dolphin vocalizations in case you don't know anything about them, and then I'll proceed to the part about how can we detect dolphin vocalizations within a recording, and then how can we extract the pitch, and then I'll follow that with some conclusions. So again, the goal of this, because I have no, can't see there, the goal of this work was to compare and come up with different schemes for the detection and pitch extraction of dolphin vocalizations, and specifically social vocalizations in long recordings, with the hope that sometime in the future people can come together and scientists can come together, collect the right type of data, and come up with some sort of contextual analysis of these vocalizations to see if there is any type of intentional communication within dolphin calls. Dolphin vocalizations in general can be classified into two broad categories. The first types of vocalizations are ones used for navigation or foraging, which is actually finding food. And those are based on echolocation, which is the sonar, and they're called in the field clicks. Clicks are basically trains of pulses, and they appear as energy throughout the frequency channels in the spectrogram. So clicks have been used for localization or for population measurements, or even I know Hervé and your team is working on some methodologies for actually coming up with the size of an animal using clicks. So clicks do have and can offer a lot of information, but they are not the ones that, according to the marine biologists, they're not the types of signals that might have any type of social information. Those are what we call social vocalizations. So dolphins have social vocalizations as well. The social vocalizations can be again grouped into two main categories: whistles and bursts. Whistles that appear as narrowband and tonal signals. These are the whistles. And they do have harmonics. These are highly amplitude and frequency modulated signals, right? And then we have bursts. Bursts are the wideband signals that are highly harmonic. Right here, this is a burst, this is a burst. And these are the two main types of signals that dolphins use for social vocalizing. There's more, there's other stuff that's called squawks and pats and all sorts of other things, but these are the two main ones. And there is actually a big debate in the marine biology community as to which of the two carries most of the information. So a lot of people feel that whistles are the ones that actually serve the purpose of an identifier. It's as if every dolphin has a name, or every dolphin provides information about their status, right? So this is a big issue in the field, right? So the field is divided, but they all seem to agree that whistles and bursts are the ones that are mostly used for social interaction within the species of the bottlenose dolphin. Now, dolphins can vocalize in a huge range, right? So anywhere from 1 to 150 kilohertz, which is extreme, but social interaction and social vocalizations are usually found below 40 kilohertz. So what about how I had to do this? Okay, and what type of data did I have? So we When you're dealing with marine mammals and you want to do any type of passive acoustic analysis, you're faced with one big problem, and at least I was faced with one really, really big problem at the time. This was a few years back. And the problem was, how do I get data? Who has it? And is it good quality of data? Right? So as I was looking around, I realized, and talking to other scientists and marine biologists and animal cognitionists, that there's two types of data you can use. You can use data provided from captive dolphins, right? Recordings that you get from aquariums, or you can use wild dolphin data. Now, there's pros and cons for each of the two types of data. And in terms of captive dolphin data, the advantages are that you're in a controlled environment. You can actually control which dolphin vocalizes, who you leave into the pool, who you don't allow into the pool. You can tag things, you can see who's vocalizing at what point. The disadvantage is that it has been shown through research that the marine biologists have done that dolphins in captivity vocalize less. And not only do they vocalize less, but their frequency range gets diminished. Because what they try to do, and this is just a hypothesis, is they try to mimic their trainers. So they try to mimic the human range of vocalization. Okay? On the other hand, when you're dealing with wild dolphin recordings, then it's like, it gets pretty difficult because you have multiple, not just dolphins, but other marine mammals present. You have boats that are passing by, you have engines that are turned on, a lot of noise, and the behavior of the actual dolphin is very different when it's in the wild. So dolphins vocalize in a different manner, they vocalize way more, and of course it's really difficult to be able to track or get any type of ground truth or data on who's vocalizing at which point, because you don't usually have visual interaction with the dolphins while you're recording them in the wild. So in my case, and trying to get some data, I was very fortunate to get some captive dolphin recordings from Dr. Diana Rice, who is a known animal cognitionist. And we got some data from the aquarium in Boston of captive dolphins. And I also was able to get from Cornell, because they have a database of animal sounds, I was able to get about an hour of wild dolphin recordings. So I chose, and we chose, to actually use and do the analysis on the captive dolphin recordings. And this was a decision that was made not only in terms of, okay, let's try and actually see what we can do with the easiest type of data that we have before we attack the toughest one, but also after having discussions with animal cognitionists and marine biologists who advised us to start from the captive dolphin data instead of actually going to the wild dolphin data, because that was something that was more controlled. So I had about 3 hours of recordings. I was able to manually extract 200 bursts and whistles and label them on a per frame level and extract the pitch per frame and some other statistics that were needed for the experiments that we were doing. Yes?
Is the database available somewhere?
Huh?
Is the database available somewhere?
Yes, anybody who wants anything, they can just email me and I'll send them everything. Not only that, I have stuff that I've bought from, because you have to pay for these. Nothing comes for free, but I have stuff that I've bought from Cornell that as long as you tell me you're using it for research, it's all yours. You can have it.
Excuse me, just for a question, if you can take the mic because of...
No, I can hear it. Oh.
It can be used for benchmark for the gym, so it should be good.
Yes.
In order to compare your results with...
Switch
on. Available at any point, any time, whoever wants them. Okay. So going through the data again, some of the things that we see is that both whistles and bursts have an average length of about half a second. And the peak SNR for the recordings was around 12 dB. And of course, one of the big differences between whistles and bursts is their pitch. So we see that for whistles, the pitch is centered around 7 kilohertz, while for bursts, it's the contrary, it's very low, it's around 700 hertz. So one of the desires behind this project was to actually try and either manipulate the algorithms that people were already using in the field and try to make those better, or to whatever we provided to make sure that we use our data to their rawest form, that we don't process them too much. Because the idea was that we wanted to be able to provide a list of algorithms that people could use on the field, for example, when they're out on the boat and they don't have enough time, or they don't have enough ability or machines to, you know, do a lot of hard processing. So the features that we chose for the different classification schemes were all geared towards that. Something simple, something that does not require too much work. Also because we were trying to keep in mind that the people who would be using this tool are not necessarily people that are trained in either signal processing or any type of machine learning. So that was the idea behind it, try to keep it simple. So the simplest, of course, feature is the spectral magnitude, using just the spectrogram. The other thing we used, which was widely used in the field at the time and still is the energy summation, which is basically collapsing the spectrogram, just adding, you know, the square magnitude for each frequency channel, and that's what they would dub as an energy summation, and that's what they would call it in the field, and they'd use that mostly for detection. And then trying to take advantage of tools that have been already used successfully in audio and specifically speech. We also decided that because we see this huge difference in pitch between whistles and bursts, that the Cepstrum might be a really good feature to capture the pitch, and thus it might be able to provide us a really good discrimination ability for detection and for pitch extraction. So we used Cepstrum coefficients. This is the real Cepstrum that we took, so that we can actually take advantage of the deconvolutional properties of the Cepstrum and highlight that pitch peak, right, to help us. And based on some other algorithms that were used for pitch extraction in music and audio, a modified version of the short time autocorrelation function was also used as a feature for some of the methodologies that we used. So, as I mentioned before, energy thresholding was and still is the most popular methodology for detecting calls in the passive acoustic community for marine mammals, as it is now. We wanted to take that and actually see how good it works, how bad it works, why do people use it, why don't they use it. So in order to provide a single index on the ability of the classification of each algorithm, we use the area under the ROC curve, which is it's an okay way to actually tell somebody, okay, this is how good the system works. So for the energy thresholding, what people do at this point is it's a semi-automatic way. So somebody will be sitting on the boat looking at the recording and will manually set a threshold that would satisfy whatever it is they're trying to extract. So that's what's happening in the field right now. And if you use an average threshold from whatever data you have, then with that methodology, what happens, you get a classification, I guess, efficiency of about 76 to 77%. But it's really biased on what's happening in the background, right? If you have a lot of clicks, remember I told you clicks are these pulses, right? All these trains of pulses, and they have energy throughout the frequency channels. So when you're collapsing the spectrogram, they will appear as a call. So you'll get a false positive there. So if you have a lot of stuff happening in the background, so it's very likely with this type of feature, they will be picked up in the detection process, right? Yes?
Can you define how you consider detections in your signals?
Whether you found a burst, a whistle or not?
Yes. I think there is a frame, there is delay when you consider that detection occurs or something like that. Is not how you consider a detection occurs.
So a detection occurs if the energy is above a specific threshold, right? That threshold,
okay.
That
no time constraints on the detection.
so in the field, what's happening, so you're using spectrogram, right? Your spectrogram is 512 with a 50% overlap, so you're looking at an 11 millisecond time window at a time, okay? So you're using the spectrogram, so there is a window that's actually being propagated. But in terms of overall of the detection scheme, in the field, what they do, there is no, that's why I said it's semi-automatic. It's, you know, they manually go in, they actually select if they want a window, and then within that window, they will tweak the threshold to extract what it is that they want, which is not very efficient, right? And it's not a robust way of actually detecting anything, but it works for them. And that's, you know, that seems to be one of the problems, is that they're used to a specific way of doing things. So energy thresholding is an okay way of doing things, but it could be better. How can it be better? Well, we see that there is this bias because of the different frequency channels. We also notice or think, we're like, well, maybe some of the frequency channels carry more information than others, right? So maybe instead of collapsing everything and then adding all the energy from all the frequency channels that might actually, give me those false positives, maybe we can take advantage of the distribution of the energy across the different channels for the different vocalizations, for bursts and whistles, right? So how can we check for that? Well, the way we did it is we checked how good each frequency channel is in classifying, is in detecting. And we did that by measuring the area under the ROC curve for each of the frequency channels, right? So what came out was this function, which is a function of the AUC, the area under the curve, with each frequency channel. And what you see there is that basically for the different vocalizations, it looks like a lot of the energy is centered around a specific range of the frequency channels, right? That also has to do with the fact, if you looked at the spectrogram, you know, there was a whistle centered around specific frequency channels. So how do we take advantage of that? Well, you can either say, okay, just sum up frequency channels, you know, from 5 to 7 kilohertz. But that would add another threshold, right? That would add another free variable in the system. So the thinking was, well, maybe there is a set of optimal weights with which we can multiply each of the frequency channels to showcase and highlight those channels that have most of the energy and suppress the ones that don't have most of the energy. And then take the summation and then do the thresholding with the energy thresholding. So we said, okay, let's try and do that and use gradient descent to do that. Right? So, which is an optimization technique, and find that set of optimal weights. So we use two types of gradient descent. We use the simple gradient descent, which is basically implies that your data is linearly separable, right? And to have a more generalized overview and allow for nonlinearity of the data, we just use the sigmoid function that gives you a smoother and nonlinear separation ability for the data. So,
can you tell us what is exactly your T and your X?
T is the target, right? It's the target. So think of it as a network, right? And you're trying to minimize this error function for gradient descent. So T is your target. It's what you would want to get, what your output, whether you would want it to be a call or a not call. And then W is the weight. It's that weight that you're trying to find.
X
that would be
just your training data.
Yes.
So you do classification with the
so this is
by minimizing the
so you're minimizing. You're trying to find that set of weights, right? That would make the discrimination even better. So we did that for the two types of gradient descent, and we applied that on the spectrogram and did the simple energy thresholding, and we did find an increase in the classification efficiency, right? From looking at the area under the curve. So we see that especially when you substitute and use the sigmoid function that allows for those nonlinearities in your data, then you have about an 83% efficiency in your classification, which is what, like an 8% increase from what we were getting. Yes.
Did you try any regression terms in your penalty functions like L2 norms or L1?
This was a long time ago, right? So it was all about just, there was no sparse coding yet. So for optimization, no, but what it was all about at the time, it was all about what your step was, right? Your learning rate, so that you don't fall and get trapped into a local minimum immediately. So it was more about trying to find the best initialization and learning rate. But that's, adding those norms, that's definitely, the regularization terms, that's definitely something that can be used now to adapt, or, there's a lot of things that can be done now. So, the same procedure exactly was used with the Kepstrom and the Kepstrel coefficients, and we used 50 coefficients out of the 257 that you get when you apply the real Kepstrom on your signal. And we used 50, and that was chosen empirically because we saw from measuring the area under their curve as a function of the number of coefficients that you have for the Kepstrom, we saw that after 50 we met a saturation point. So there was not much difference on how well it classified. So when you use the Kepstrom and you actually sum the Kepstrom, so it's like using the energy feature only with the Kepstrom and you sum it, then you don't have the same type of success. And again, I think that's somewhat expected because you don't have, when you're collapsing the Kepstrom, because you do have a lot of averaging of the signal, then that sort of takes over. And that's what diminishes the ability for the Kepstrom to discriminate when you're collapsing it, right? When you're actually summing it. To, I think, answer to yesterday's question about why not the Mel-Kepstrom, because that was a discussion we had also. That's why I'm bringing it up. It's not just here. So at the time when Professor Ellis and I were talking about this, we had the same debate. Why not use the Melkepstrom, or why use it? And I think what we decided is that the Melkepstrom is tuned to speech, right? So it's basically trying to apply a model to a mammal when we don't have all the information about how that specific marine, how the dolphins process sound, what are the transfer functions that you can use, or the filters that they use to process sound. So that's why we opted to just use the Kepstrom. So I don't know if that was the right decision or not, but that was the thinking behind it, and I'm only mentioning it because we had the same debate as to why or why not. So the next step was, well, okay, we're saying that the energy thresholding is working. Well, we have a two-class problem. It's a binary problem. We want to see if we have a call or we don't have a call. What's the simplest thing we can ever do? And that's fit a normal distribution in each of the classes, and then do maximum likelihood. See which one, you know, which likelihood is bigger, then that's a call or it's not a call, right? So that is the simplest thing you could possibly do. It's efficient, especially if you have the data, and that's what we did. We just fit one distribution for each of the two classes. We actually did try to see if more components would help, especially because for your call class, you have different types of calls. So we wanted to see if EM would be able to capture those different types of distributions. And it did partially, but we didn't see in the overall detection scheme, there wasn't much of a difference if you used multiple components or not. So we figured the easiest thing was to actually use the simple distributions fitted on the data. We did the same thing for the spectrum, for the spectral magnitude, and for the Kepstral coefficients, using 50 coefficients again. And we saw that both of them worked really well, and the efficiency of the detection scheme was over 80%. So for the spectral, you had about 84, and then for the Kepstrom, you had about 86. Because our data was moderate sized, right, we didn't have a lot of data, sometimes issues creep up where you might need to normalize or standardize your data so that you can make sure your covariance matrices are positive. So that's something that's unfortunately related to how much data we had. Those are issues that came up a lot when we were working. But that's something that at least now that we've been able to collect a lot of data, that's good data for the past, 3-4 years, I think, it's something that can be easily overcome. So the next step, and mentally, was, well, if the distributions and modeling my data using simple Gaussians is working so well, why not use a support vector machine? And why not use an SVM, which is a discriminatory type of method, but why not use that with a radial basis function, right? Like a Gaussian kernel. That should do the best out of everything, right? And it did. It actually did. So, but, you know, the problem with SVMs is, again, that you have that almighty trade-off between computation and accuracy, and that's also a theme within this work, which was, well, let's try and see how we can find a balance, or what works best but takes the longest time, and vice versa. So, support vector machines were used both on the spectrogram using the spectral magnitude and on the 50 Kepstrel coefficients. And they were pretty similar, really, really good in terms of efficiency of classification at around 95, 96%. They were actually, those are the ones that I used on the wild dolphin recordings because I had to see and test a little bit the limits of the SVM, and they did do okay, not close to 96%. I'd say on wild dolphin recordings, they, for the detection task, they did around 70–75%, which is not bad. That was, you know, SVM seemed to work the best, and it was something that was expected given the structure and how they work. So, in terms of everything, and that was sort of the idea behind it, was to see how things fared in terms of what had the best detection rate while working the fastest or the slowest. So SVMs with the Spectrum and the Kepstrom fared pretty much the same, but were the most computationally expensive. Gradient descent with the Kepstrom was actually the one that did the worst. But overall, I think we provided for the field a medley or a better understanding of what could possibly work and what they could possibly do, instead of just sticking with the energy thresholding, and how with some little and subtle changes they might be able to actually increase their ability to detect better within the recordings. So that way, if they're on the boat and they actually have the ability or Wi-Fi to send the stuff out in the lab, they can possibly do SVMs. But if they're on the boat and they don't have that ability, they can do their energy thresholding with a little bit of a tweaking to get a better detection rate. Again, this is just indicates the difference in terms of that trade-off between computation and accuracy. Yes, SVMs are great, but they take a long, long time. So that's something somebody needs to take into account when they're actually using it. Yes?
The time for the SVM is just time for training time, but when you have to do classification, it's...
Yes, this was just for training.
Yes.
Yes.
So
once you do the training, then you can use it, then you're fine. But, you know, thinking again, this was for me to provide an understanding for the people in the field. Yes, you can do this once and then do it. But the other thing is, as you're getting data in, right, ideally you'd want to retrain your SVM.
Yeah.
So that's why this was just so that they have an understanding. That's not something they can use on the fly. They'd have to actually go somewhere and train it. They can do it on the... So once you have that detection ready, the next step and the next big issue in the field was, well, we want to actually extract the pitch of these vocalizations. We want to get either the frequency contour or the pitch. How do we do that? And what people had been doing and are still doing is they just do a template matching. So they will actually manually create a little kernel that will resemble, using sinusoids, right? They will resemble the whistle, and then they would cross-correlate that with their signal, and wherever they will get peaks, they'll say, oh, I found it, I extracted my frequency contour. So this is what people do. Again, it's a very non-optimal way, but it's been working for them, and it's hard to get them to find other ways of doing it. So one of the things we were thinking of doing is, well, let's assume that our detection is done. So we know that we either have a call or we don't have a call. We have those segments extracted. Well, if we look at our data, and you can see a histogram there to the right, and that's on the pitch delay, which is why they're reversed in terms of frequency. But if we look at the pitch of our data, of our calls, we see that there's an inherent bimodality, right? And that's something, because I mentioned in the beginning, well, you have calls that are whistles and you have calls that are bursts. And those two types of calls have two very different types of pitches, right? One is centered around 7 kilohertz, the whistles, and the bursts are centered around 700 hertz. So that's why you see that separation. It's like a camel, like two humps, right? So there's that bimodality, and we figured, well, is there any way we can take advantage of that to help with the pitch tracking? And I think I'm missing something. Sorry. Yes. So we said, well, let's use a generative model. Let's use hidden Markov models. That's something that's been widely used in audio and speech and music. It will capture those temporal dependencies that we have, right? Because when we're looking at a whistle and we're looking at a burst. So let's use a generative model, and since we're dealing with pitch and pitch extraction, we'll use the Kepschel coefficients as our feature. Let's compare that with what's out there already. So we compared it with Alain de Chevigné, I hope I'm saying it right, Yin, which is a very good algorithm that's been used widely in music and speech for single pitch extraction. And we also compared it with an off-the-shelf package called GetF0, which has been used for speech extensively, and it's based on the LPCs for extraction of pitch in speech. So again, as I mentioned before, we wanted to take advantage of the bimodality in the data. So we said, okay, maybe we can break down our state space, right? And we can have two different ranges and two different HMMs. One HMM to deal with whistles and one HMM to deal with bursts. So we said, okay, let's try that. Let's use a hierarchically driven HMM. And what we should do is every time we have a call that comes in that we've detected, but we don't know what it is, let's evaluate the HMM to decide which model it fits, right? Does it fit the whistle model or the burst model? And then once we have a decision, and hopefully it's the right decision, right? Then we can use Viterbi and decode and actually get the pitch. That was the thinking behind it. We had to get the ground truth. That was gotten in a semi-automatic way. We worked on pitch delays, and we used de Chevigné's Yin to actually get our ground truth, and then manually corrected any other mistakes. We had two HMMs, right? So we created two HMMs with two different types of state spaces, different ranges of state spaces, one for whistles and one for bursts. And then...
Why do you need so many states? 52?
Because bursts tend, it has to do with how the actual, the nature of the actual signal. So bursts tend to have more differences that are slight and more important. So they actually require more states. So it really has to do with the nature of the actual signal that you're trying to model.
Trading is more difficult. More data.
Yes, so you need more data. That seems to be the theme. There is need for more data, and at least it was for me when I was working on this. That's something that thankfully now is not a problem. At the time it was, but it's not a problem anymore. So that was our methodology, and we compared that with Yin. Yin is based on the short time autocorrelation, and what de Chevigné does is he creates a weird difference function based on the short time autocorrelation. And then what he tries to do is minimize that difference function and pick the lowest delay value, and that is your pitch, according to his methodology, which actually has a very successful accuracy for single pitch extraction. And then, as I mentioned, we compared that with GetF0, which is just an off-the-shelf. This is a plug and play, and it's very, very tuned on speech. So it's not exactly the best thing to work on when you're dealing with dolphin vocalization. So the results for the frame accuracy, and what we did is we devised a little bit of a leeway for us. So we came up with three types of rates. One is the strict rate, so that you have the correct extraction of pitch at every frame, and then we relaxed the rate a little bit so that we allowed for some sort of deviation, because it's something you can smooth out, you can interpolate between the different, because you're discretizing your pitch, right? So you can actually maybe perhaps allow for some fuzzy boundary between your extraction. But sticking with the strict rate, I'd say that the hierarchically driven HMMs did outperform Yin, but they did not, to my personal opinion, do fantastically well. We got in about 66% of accuracy, and that's not including the range error, right? So when you're actually evaluating each HMM, it doesn't mean you're always going to get it right, that it's a burst or a whistle. So to have a better look, and I don't know, you probably cannot see, but this is the ground truth. This is a whistle, this is a burst. I know interlacing from the projectors is awful, but this would be the result of the Yin, this would be the result of the hierarchically driven HMM. There are some deviations, and there are some issues that we see, especially with Yin, because there are some doublings and some halvings of the pitch. A better way to visualize it is here, where you're actually seeing the rates one versus the other, and what you want to see ideally is everything towards this end of the corner, so that you can actually have that high frame rate that you want to see from the HMMs compared to the Yins. And the ones that you see all the way on this side, these were the ones that were misclassified by the evaluation of the HMMs when we had to decide if this was a burst or a whistle. And overall, I think we had about a 4 to 5% range classification error, which is significant, I'd say. So the final system was based on a probabilistic framework and Bayesian inference. And what the idea behind it was, well, let's focus on whistles. If whistles are the important signal in marine mammals, and that's where people think most of the information is, then those are the ones we need to try and extract. So we figured, okay, let's create a system that will allow us to get the highest likelihood of a call structure given our observation. The system was broken down into two subsystems, right? The front end, where basically you want to find the probability of your observation given an ideal signal, right? Because your observation is going to be your ideal signal plus some noise that you're going to have, right? So the front end, which is basically trying to extract segments from your spectrogram, like little pieces from your spectrogram. And then you have the back end. And can you guess what the back end is all about? It's about trying to put those little segments together, right? So that they can form a call. So in order to do that, and it's something that has been done with again, widely in speech and audio in general, which is basically sine wave modeling, right? What you want to do is extract those regional maxima at every time frame within your spectrogram. So you're dealing directly with the spectrogram. So at each time frame, you want to extract those little peaks. Now, those little peaks, when you're just extracting them, you're going to get a lot of false positives because you have a lot of noise. You have all sorts of things happening in the background. You have the clicks, you have the engines, you have gazillion stuff, or reflections from the pool. You have a lot of things happening. So there are ways or hybrid ways to actually try and minimize that those false positive regional maxima that you get. And we used like an iterative algorithm. It was sort of handmade and based on data that we had already, and it was based on the variance of the regional maxima within each time slice, right? So you use that as a threshold to be able to eliminate and denoise each frame for most from your false positive regional maxima. So once you extract the thread, the maxima at each time slice, then you have to thread them together and interpolate, you can use different stopping criteria which determine how long these segments are going to be. So if you can't thread your regional maxima after a specific time period, then you can say, well, this segment has ended. So once you have extracted and you've threaded that maxima, you now have something that looks like this. And I know you can't see it very well. The circles only indicate the beginning of each call. So this is a whistle, and these are segments that have been extracted from the whistle. The same here. You can probably see it better on the paper than on the slide. So once you have those segments extracted, now you have to connect them. And here's where things become a little bit more difficult, because you can have all sorts of discontinuities, right? So you can have a discontinuity within a single call, right, a single segment, or you can have discontinuities between multiple segments. The first part, having a discontinuity within a single call, within a single segment, is something you can actually alleviate fairly easily. Again, because all you need to do is say, okay, I have an erroneous, a wrongful gap within my segment, then I know that my segment on average needs to be this long because that's information I get from my data, right? So I'm just going to interpolate and connect that. So that's the easy part when you have within a segment, when you have a blank. The difficult part becomes when you have what's called intercall discontinuities, because now you have multiple options, right? So you might have one segment, right? And then you might have other segments here, right? So you might have multiple paths that you can connect to, and you have to find which path is the best. Or you might have a single path, and you still have to decide, well, is this a good path to connect so that I can get my call? Or you might have something that's completely alone and has nowhere to connect to. So those are the three broad possibilities that you have. So the way we dealt with this is we actually, you know, you have to search for all these paths. So we created a grid neighborhood, again, based on statistics that we get from the data. This is highly tuned on the type of data that you're working on, right? So we know that the connections need to be, for example, within, you know, 1,000 hertz So within a few frequency channels, so that would be your grid neighborhood, and then you need to make sure that you're moving forward and not backwards, so you can eliminate anything that's back in time and not forward, et cetera, et cetera. So you create this grid neighborhood, and now you start looking for the different paths. And if it's a lonely path, then that's easy because you just connect them, the two, you interpolate, right? If it's that's if it's a sure path. If it's a lonely path, there's nothing to do, right? So you just leave it as that. But then if you have multiple paths, you need to choose between the different paths. Which one is best? How do I choose which one is best? So we looking at the data and just being exposed to the data and looking at the whistles and looking at the burst, one of the features that we saw that was very important, or appeared to be important, was that there was a smoothness in frequency, right, and in the amplitude and energy of the signals. So we said, okay, let's try and take advantage of that and use that as a criterion of when things connect or when they don't connect. So we use the smoothness, which is the second derivative, right, from the neighborhood of the calls, because these are calls that we already had extracted, so we had the ground truth for them. So we use that to train and make that decision whether it was able to actually connect or not based on some threshold in the smoothness of frequency and energy. So once you make the connection, and hopefully again it's the right connection, then you can always interpolate to smooth things over. So here is an example after you had the little segments. Now the segments are connected, it will again capture, you can't see it very well, it will capture a good amount of segments. Again, you have two different types of issues that creep up. You have the first issue of actually locating the right segments, and then you have the second issue of actually connecting the right segments together. So this is a simple example when you have no overlaps. This is an example where you have an overlap. This is something that came out of this work that we thought was important, which was the hope that we would be able to decipher between overlaps. And by overlaps, I mean, well, dolphins tend to not be very polite, right? So they like vocalizing on top of each other. They won't wait for the other dolphin to finish. So one of the hardest problems that people face is trying to automatically decipher those overlaps and see, well, does this belong to this call or the other call? What's the best thing? So we were hoping that this might be a first step to actually try and resolve these overlaps, because you're using that framework and actually taking advantage of characteristics that you find within the signal. So let's see how we did in terms of the overlap. So it actually was able to decipher between what I would call a simple overlap. And a simple overlap is one where you actually do have, remember, we're using the smoothness in frequency and energy, so you want to have that indicated within the spectrogram. So that's what I call a simple overlap, right? So where you see it looks like a cross almost. So there is a huge difference between the direction within the frequency of how things are moving. So that's why it's able to decipher that overlap. But on the other hand, this one, which would also appear as fairly simple, it's not being resolved. And if you were able to look closer, which I know you can't because of the way the projector works, but you'd be able to see that there is a click. Actually, there's a couple of clicks that are hitting the overlap right behind it. So that's energy that's being picked up, so our criteria is not able to actually resolve that. So it's a miss, but at least it was a first step in trying to get an understanding and using some characteristics of the signals to try and find ways to resolve those overlaps. So again, as I mentioned, there are two types of issues that you need to worry about. First of all is getting the right, extract the right calls on per frame and the right segments and connect correctly. So we got about an 80% in extracting the right stuff. Again, because you had those errors, and then we had a really high rate, over 95%, is it? Yeah, 97% for connecting the segments. But that's biased because our system was biased. It was biased to connect, right? So more characteristics, more information needs to be extracted and used in order to be able to get a more accurate version of how things connect. This was a first attempt in actually trying to provide some sort of overlap resolution. So the system on the whistle extraction, again, yes, it does manage to resolve simple overlaps, but it's only on whistles. Right? It will work only on whistles, not on bursts, and sometimes you do have overlaps of burst with whistles, so nothing is going to happen there. The system is not able to handle that. Only handles whistles. And the system on the whistles and the bursts with the hierarchically driven HMMs assumes that the detection is complete. There is no overlap resolution, which is where you will get errors again if you have multiple signals that are on top of each other overlapping. That system will also have those range errors that we talked about at about 4 to 5%. And we were able to compare with some baseline systems. And finally, as far as the detection, again, the goal was to provide a medley of systems to the field so that they have a better understanding of what it is they can use, what they're using now, and how they can better that. And for pitch extraction, again, we wanted to give them something that they can use for whistles and bursts with no overlaps, and a first step on trying to resolve overlaps in whistles. That's it. Questions? Yes? No? That's it.
I think about the pitch extraction, there is maybe this particle filtering approach that could be interesting.
Oh, I think there's many interesting approaches that can be used.
Did you consider the...
No, we did not consider particle filtering at all.
Why not?
No, I don't think it was something that...
to track a peak.
It was not something that at the time we were focused mostly on our sine wave modeling. And
yeah, this was more Baker thing.
Am I saying it nicely?
You remember Baker work on sine wave?
Am I saying it polite?
This was I see.
Yes. Advisors tend to like what they like. I see people smiling, I can tell they're getting their PhDs. But, yes.
From figures on pitch extractions, it seems that the whistles, they would go higher if you could represent them, because your sampling frequency doesn't allow you to represent anything over 22 kilohertz. So
yes.
Wasn't it a problem for you?
That's that is a big problem. So if you remember one of were you here or you came in from the beginning? Yes, so the second thing, my second slide was about the data. How difficult it is to get the right amount of data. Yes, unfortunately, because dolphins vocalize up to 150 kilohertz, right? But we don't have that ability, at least as far as I know. I know Jani Kavan is the one who's getting the best type of recordings, and he's using 90-something sampling frequency. What is he using for his hydrophones? So he has the clean. Oh, so he has a 44.1.
Yeah.
He used to have higher. So we tend to get a lot of things that are either left out or aliasing, you'll get some aliasing, a lot actually. So these are things you have to take into account, unfortunately. It's one of the curses of working with these types of signals. Am I moving too much for the camera? Thank you. Yes?
I've got a question, maybe two. The first would be, can you remind us the slide about the third application about burst detection, something like that? No, pitch detection. You know, when you use JMM models and HMM, you know, like in speech processing.
Oh, so yes, so
Just before this pitch extraction.
okay, so
Yeah, something like that.
yes.
Of course, you can try everything, but after maybe you would be to try to more discriminative approach to replace more GMM by something like neural networks or SVM.
No, we did not. It's something that came up, but we did not. We felt that there was a need for a generative approach more than a discriminatory approach. But it's something that was discussed in terms of using other types of methodologies like neural networks or SVMs.
And on the previous slide, maybe before there was the results table, and which compare all the performances of the objective, yes, this one. And did you try for the SVM or multiple target approach in order to combine maybe spectrum and spectrum?
No,
Okay.
we did not.
Maybe,
That's something that can be.
both supports of spectrum and spectrum share the same information, or there are different information?
I think there's different information. I think the capture manages to give you a concise description of the pitch, but it's not able to capture other information that might be important, which has to do with I don't know, like slight variations in energy or something else that might appear important. So I actually think that the spectrum is, you know, and I mean the variation is really slight, right? But I think that the spectrum is a much better suited feature for this type of signal, right? That was my.
And for the last part, for the pitch extraction, I think this is maybe your hardest task in your.
Yes, that was
mainly because I have the PID on almost the same subject and can
Yeah.